Alright, so for today's notes, I'm going to be going through them on this video lesson, so just copy along with your notes paper that you should have picked up from the sub, and then let me know if you have questions tomorrow when I get back. So to start, we've got this idea of interpreting data in normal distributions. So this whole last unit is about statistics. So the first kind of new vocab word we want to understand is this idea of skewedness. So skewedness is describing how the data looks. So skewed left means it has a tail on the left side. So most of the data is actually to the right. This is called skewed left. Skewed right is when the tail is on the right side. So again, most of the data is to the left. The tail is where it's skewed. So skewed left, skewed right. And then no skew is when there is no really tail. It's just kind of normally, evenly distributed. This is known as a normal distribution or a bell curve. So if we look below, we've got these examples of some data distributions. And when we look at it, we've got this math quiz scores. Most of them are kind of all lumped to this right side. So if we look at the data, the majority is to the right, the tail's to the left. So remember, when we look at this, the tail is at the left. That would be skewed left. If we look at the number of fish caught, we've got the majority of the data on the right, or on the left, the tail is to the right. So this would be called skewed right. And then moving on, we've got another new idea. This is how different types of data. We've got factual information such as measurements or statistics are used for basis for reasoning, discussion, or calculation. Data can be discrete or continuous. Discrete data can only take on specific individual values. So like number of home runs in a baseball game has to be a whole number. Number of students in a class has to be a whole number. Shoe sizes has to be a whole number or a half. But you can't have an 8.3 shoe size. That doesn't exist. Continuous data can take on any measured value within a specific interval. So heights, you can be 5'1", 5'2", 5'3", 5'3 and a half, 5'3 and a quarter. It can be any measurement in between there. There is no set data point that you're jumping between. Time required to complete a test, right? You can complete a test in minutes, seconds, hours. There's no specific amount of set. It has to be in 10 minutes or 20 minutes. There's no intervals there. Distances between cities, right? So these are things that are just continuous. They keep going. There is no jumping point. So below, I want you to pause the video and see if you could identify these different values as discrete or continuous. All right, now that you've hopefully tried that, let's see how you did. So number of Facebook likes, that would be discrete. It has to be a whole number. Water temperature, continuous. That can fluctuate, go up and down. A number of questions on a test, that's a discrete value. That's a whole number. Time to run a mile, that's continuous. The clock is always running. Students can finish at any point. Number of votes, that's discrete. That's a whole number. On someone's weight, that's continuous. That can fluctuate. There is no set stopping interval. So then onto the back side, we've got this idea of population. Population is an entire group that you want to draw conclusions about. In research, a population does not always refer to people. It can be objects, events, organizations, countries, species, etc. A sample is a specific group that you will collect data from. The size of the sample is always less than the population. but the sample is going to represent the entire population. So an example, a population could be all senior students at Joliet Central High School. The sample of that data could just be if we picked 100 seniors and randomly polled them. And the last idea for this lesson is this normal distribution. So one way to display continuous data is to use a relative frequency table. A relative frequency is the ratio of occurrences within an interval to the total number of occurrences. You can represent this ratio as a decimal or a percent. Since relative frequencies are decimals or percents, they should always add to 1 or 100%. So down here we've got this example. 200 runners completed the annual Sundowner 5K race. The table displays the race times for the 200 runners. We're going to complete the table to determine the relative frequencies. So we are going to divide the number of runners out of the total, which is 200. And we're going to write that as a decimal. So we've got 0.035, 28 out of 200. We've got 0.14. 65 out of 200, got 0.325, 71 out of 200, gets a 0.355, 24 out of 200, gets a 0.125, and 5 out of 200 gets a 0.025. So if we add up all of those decimals, they should add to 1, and they do. So we know we've got all our frequencies correct. And then when we go to graph this, we're taking the race times 12 to 18 minutes, or 14 to 18 minutes, and we're saying, okay, that relative frequency was 0.035, so that's a little bit more than halfway there. Then from 18 to 22, that was 0.14, so a little bit below 0.15. Then from 22 to 26, we are at 0.325, so right up here, halfway. From 26 to 30 minutes, we're at 0.355, so a little above 0.355, here we go. From 30 to 34, we're down to 0.12, so we're down here. And then from 34 to 38, we're at 0.025, so a little bit lower. So when we look at this data, it appears that it is evenly distributed. So I would say this data has no skew. It seems to be even on the left and the right sides. There's no specific tail. So the next thing I want you to do is go to Google Classroom and try out the quizzes just to really test your knowledge of relative frequency. And then come back tomorrow with questions, anything you guys want to go over. Thank you.